Hello students, in today's lecture we are going to learn about electric charges and fields, and this is theory part. Disclaimer: the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the content immediately. Please note that parts of the content may have been generated using generative AI, which is experimental. In today's lecture, our topic is electric field due to an infinitely long straight charged wire, or we can say infinitely long straight uniformly charged wire. So we have to calculate here electric field at a given point. So look at figure A and figure B. So in figure A, it shows electric field due to infinitely long straight wire is radial, and we have a charged wire. Look at here, this wire is charged, or we can say positively charged wire, and here we will calculate at point P. At point P, what is the electric field at point P due to this infinitely long straight uniformly charged wire. So the case describes an infinitely long straight wire with uniform linear charge density lambda. So what is uniform linear charge density? So we know lambda is charge divided by length. Lambda is what? Charge divided by length. So what will be the total charge? Charge equal to lambda into L. Lambda into L. Due to symmetry around the wire, suppose at point P, if we talk about the two-dimensional plane and we rotate point P like in anti-clockwise direction, it form like circular shape. Circular shape. At point P, at point P1, at point P prime, at point P double prime. The electric field, listen carefully, the electric field due to all these points P, P prime and P double prime is same, because their radial distance from the point, or we can say from the point to charge wire is R, and it is same in at every point. So at P prime, P double prime, it means the value of electric field at point P is equal to the value of electric field at point P prime. Similarly, the value of electric field at point P double prime, because this is having symmetry shape. So due to symmetry, we know P prime and P double prime obtained equal electric field at given point. So rotating the radial vector, by rotating the radial vector, so the value of electric field will be equal. Now here question arises, what is the direction? So the direction of electric field, how we can determine? Suppose we have to calculate the electric field at point P. Here charge is positively charged. If we consider a small region, the charge is positively charged. It means the lambda, the linear charge density, should be positive. So if the lambda linear charge density is positive, In that case, the direction of electric field radially outward. And what about the negative charge, or we can say if the linear charge density is less than 0? If the linear charge density is less than 0, in that case the direction of electric field is radially inward. How we can understand the radially inward and radially outward? So from point O to point P, O to P, O to P, look, listen carefully, point O to point P, towards point P, so it is radially outward. And from, if we talk about the radially inward, from point P to towards point O, so it is radially inward. Now in our case the wire is positively charged, so in that case the direction of electric field is radially outward. The direction of electric field is radially outward. I hope this is clear. Next, we calculate the electric field at point P. For line elements P1 and P2, so there is a two line element. The P1 line element, so what the small region, or we can say small line, small part of this infinitely long straight wire we known as here line element. So the line element P1 and P2 and their combined electric field gives a radial resultant as normal components cancel. So here we calculate first at point P electric field due to infinitely long straight charged wire. Now here is one important point is, look at here, if we talk about a point, the position of point P is changed. Suppose the position of point P is this one. Now the position is changed and it will be N point. In that case, what will be the electric field? So the electric field will change because it depends on the radial distance. It depends on only radial distance r, not position along wire. So it depends on r. So let's see the electric field at point P. So for calculating the field, consider a cylindrical Gaussian surface. So look at figure B, this one. The infinitely long straight wire, or we can say infinitely long straight charge wire is this one. And here we consider a Gaussian surface. The dotted region, this region is a Gaussian surface. Now the point P from the charged wire at a distance r. So there is a three surface. First is the circular, second is also circular, and third one is curved. Here we neglect the end points. Why we neglect here? Because the wire is infinitely long. Due to infinitely long charge wire, the effect of electric field is negligible. So we will calculate only we calculate only for small line element. So the radial field means zero flux through cylinder ends, because we neglect here if there is a no electric field, so flux will also here zero. At the cylindrical surface, the cylindrical surface is this one. Look at here. This is the cylindrical surface. The length of the cylindrical surface is L, and electric field is perpendicular. Why perpendicular? Because the charge is positive, and due to this positive charge, the direction of electric field is radially outward. Radially outward. Now surface area of this curved region is 2 pi RL is 2 pi RL. So the flux through Gaussian surface equals flux through curved cylindrical part. So what is the flux? We know the formula to calculate the flux, that is phi equal to what? Phi equal to E dot ds. Yes or no? According to Gauss theorem. Now we resolve the dot product. You will be get phi is equal to E ds cos theta. Cos theta. And what is the theta? How we can calculate the value of theta? So to calculate the value of theta, we know the direction of electric field is radially outward. Radially outward. And the area vector is also perpendicular to line element. So this is the direction of area vector and this is the direction of electric field. It means what? It means direction of electric field or direction of area element both are parallel. Yes or no? Both are having same direction, or we can say both are parallel. If both are parallel, in that case theta should be 0 degree. Yes or no? So theta is 0 degree. Just substitute the value of theta in cos function. So you will be get phi is equal to E ds. Cos 0 1. And what is the value of ds? And the value of ds is area of curved part. And what is the area of curved part? That is 2 pi RL. So just substitute here. You will be get phi is equal to E into 2 pi RL. 2 pi RL. So this is the electric flux through Gaussian surface. Clear? Now for charge is lambda L. So here we talk about the wire, or we can say infinitely long straight wire. So here we will use the concept of linear charge density, that is lambda. So we know linear charge density lambda is equal to what? Charge upon length. So if we want to calculate the charge, it will be become charge equal to lambda into L. So lambda L is the charge enclosed by this Gaussian surface. Clear? Lambda L is the charge enclosed by the here. Q is equal to lambda L is the charge enclosed by this Gaussian surface. Now we will use the Gauss law. So Gauss law is total charge, this one, total flux is equal to total charge enclosed by the closed surface. So here total charge is what? Enclosed by the closed surface is lambda L. Yes or no? Divided by epsilon naught. So according to Gauss law, the total flux passing through the closed surface is equal to the total charge enclosed by the closed surface divided by epsilon naught. And we know the value of lambda L. So value of lambda L, value of Q enclosed is lambda L. Clear? Now substitute the value of Q charge. So it become phi is equal to Q enclosed is what? This is lambda L. Lambda L and divided by epsilon naught. Clear? And what is the flux? We already calculated this. This one E into 2 pi RL. So when we substitute the value of phi, you will be get E into 2 pi RL is equal to lambda L divided by epsilon naught. I hope now this is clear. So what is the value of L? How we can calculate E? So solving this, you will be get value of E. So therefore the value of E is equal to lambda divided by 2 pi epsilon naught into r. R is the point. R is the point from this line element. So this will be electric field at point P, and direction is radially outward. Direction is radially outward. This one in outward direction. Now if we talk about the electric field at point P prime, what is the value of E and what is the value of electric field at P double prime? Think about it. So the magnitude of the electric field at point P prime is lambda divided by 2 epsilon naught r. Similarly, magnitude of electric field at P double prime is same because it form a circle. Now here important point. Look at this expression. This expression E is equal to lambda divided by 2 pi epsilon naught. So how we can change the value of E? The E depend on lambda and E depend on R. Yes or no? E is here, E is directly proportional to lambda and E is here inversely proportional to R. Yes or no? And where we know lambda is what? Lambda is equal to charge upon length. If the amount of charge enclosed by this closed Gaussian surface is increases, in that case the value of lambda is also increases. Yes or no? And if the value of lambda is increases, in that case what will be the change in the electric field? Or we can say what will be the change in E? E will also increase. So this is our first case. Now in second case, if here look at here, E is inversely proportional to R. Now if the value of R is increases, in that case what will be the change in electric field? The value of electric field is decreases because here E is inversely proportional to R. Now if we talk about the value of E from this relation, it is inversely proportional to R. If R is increases, E decreases, and if R is decreases, R is the radial distance. Look at here, R is the radial distance from the line element at point from line element to point P. So if R increases, the value of E decreases, and we can say in second case, if R decreases, in that case E increases. So this is very important concept. Clear? And how we can draw a graph between E and R? So look at here. First of all, we draw axis. So this one is x-axis, or we can say R x-axis, and this one is y-axis. So here E is inversely proportional to R. So this is R, and here it is like this. This one, E and R. If the value of E increases, the value of R decreases. Both are inversely proportional. I hope now this is clear. So if we see it vectorially, the E is equal to lambda divided by 2 pi epsilon naught R n cap. Look at here. This value lambda divided by 2 pi epsilon naught is the magnitude. Clear? And the n cap is what? N cap is the direction. We know the direction of electric field is radially outward, and the direction of area element is also in outward direction, or we can say perpendicular to line element. So this is the in vector form. E is equal to lambda divided by 2 pi epsilon naught R n cap. Clear? Where n cap is radial unit vector normal to wire at that point. Now here n cap is unit vector. It means we can resolve unit vector like n cap. Suppose we have talked about the unit vector is r cap. Suppose r cap is unit vector. So we can write is r vector divided by magnitude of r. Yes or no? So similarly n cap is here radial unit vector. Now vector notation. Look at here. This is very important. For vector notation, A is equal to the A vector is equal to magnitude of A and A cap is algebraic, means positive or negative. Here the another method to write this like this. Vector A is equal to mode of vector A divide mode of vector A and unit vector A cap. Clear? And direction follows A cap if A is greater than 0 and A opposite direction if A is less than 0. Through calculation uses enclosed charge. Look at here. We know linear charge density lambda is equal to charge upon length. So enclosed charge is lambda L and electric field E results from entire wire's charge. So the infinite wire assumption ensure E normal to cylindrical surface. Look at here. The E is electric field is normal to the cylindrical surface. Equation approximately holds for central points of long finite wires, ignoring end effects. Due to the end, suppose this end and this end, the electric field is neglected because this is in endless, infinitely, as given in the topic, infinitely long straight wire. Clear? Now, here one question for you. Suppose the value of lambda is fixed and value of r is changes. In that case, what will be the effect on E? So one value, the value of lambda is fixed, constant, and only r, the value of r is increases. Suppose increases. So in that case, what will be the change in E? Think about it. If r is increases, the value of E is decreases because both are inversely proportional. E is inversely proportional to r. Clear? Here one important concept. Suppose if we talk about, listen carefully, E is directly proportional to 1 by r. So it is correct. Now if we talk E is inversely proportional to r, so it is also correct. Clear? Because in first line we say 1 upon r, complete term. E is directly proportional to 1 by r and inversely proportional to only r. So this is the main difference. Clear? Now we will calculate electric field due to uniformly charged infinite plane sheet. Infinite plane sheet. This sheet is infinite. Look at here. This is sheet. This sheet is infinite. Now we find the electric field due to this phase and due to opposite phase of this plane sheet. Suppose we have a plane sheet, this one. So there is a like a paper have a two phase. First phase is in LHS side, and second phase is this one. So due to infinitely charged plane sheet, or we can say uniformly charged infinite plane sheet, what will be the electric field at a point, or we can say at a given point. So here we calculate electric field due to uniformly charged infinite plane, and so due to we here use the concept of surface charge density, that is sigma. We know sigma is what? Charge upon area. This is the surface charge density. Now the distance from left phase to Gaussian surface. So this is, here we draw a Gaussian surface, this one. This dotted region is the Gaussian surface. So due to this Gaussian surface, the region is covered only this region. Clear? So this one is positively charged. This region is positively charged. Similarly, first phase is also positively charged. Clear? Now what will be the electric field? Let's see. The given configuration has a uniform surface charge density sigma on an infinite plane sheet. Clear? With x-axis normal to the plane. Now if we talk about the first phase, so the direction of electric field is perpendicular to the plane. So this one, electric field is perpendicular to the plane. If we talk about the second phase, so here also electric field is perpendicular to the plane. Yes or no? Now due to symmetry shape, electric field depends only on x-axis. So electric field E depends on only x-axis. So the Gaussian surface chosen is the rectangular parallelepiped with cross-sectional area A. So this one, the cross-sectional area of this region is A. So there is a two phase, one phase first and phase second contributes to the flux since the electric field lines are parallel to other phases. This is important point. Now if we talk about the second phase, so what will be the electric flux through passing from the second phase? So we know the flux is phi equal to what? E dot ds. Yes or no? E dot ds. Now solving the dot product, you will be get E ds cos theta. Yes or no? This is important formula. Now what will the value of theta? How we can calculate? So here the direction of electric field is along x-axis and area vector is also perpendicular on plane n cap. So n cap and n cap and the electric field both are parallel. Yes or no? If electric field and n cap, if we talk about the second phase, so in that case the electric field and n cap is parallel. It means theta is what? Theta is equal to 0 degree. So just substitute the value of theta. You will be get E ds. And E ds is what? ds is the cross sectional area, that is EA. So if we talk about the flux through second phase is what? E into A. E into A. Now if we talk about the first phase, the flux will be what? Flux will be same. Why same? Because here also the electric field E and direction of area element both are parallel. If both are parallel, so it means theta is 0 degree. If theta is 0 degree, it means phi 1 is EA, because we know cos 0 1. Clear? So phi 1 is equal to EA and phi 2 is also EA. Clear? So surface first has a unit vector in x direction. So x direction means like this. While surface second has in positive x direction. Surface first in negative x direction. So the flux E dot delta S through both surfaces are equal and additive. So total flux is what? E into A. 2E into A. We know because flux through phase first we already calculated is EA, and flux through second phase is what? Is also EA. So what will be the total flux? Total flux phi is equal to phi 1 plus phi 2. So add this, you will be get 2 EA. Clear? 2 EA is the total flux. And where enclosed charge is sigma into A. Sigma into E, sigma into A. Now how we can calculate the value of E? So here we applying the Gauss's law. Gauss's law. So what is Gauss law? So Gauss law, total flux, total electric flux passing through the closed surface, passing through the, or we can say passing through the surface, total flux passing through the surface is equal to the total charge enclosed by the closed surface divided by epsilon naught. Yes or no? So here what is the total charge? Here we talk about the surface charge density. So using the concept of the surface charge density, we will calculate the total charge. So surface charge density sigma is equal to charge upon area. Yes or no? So charge will be what? Charge is equal to sigma into A. So just substitute the value of sigma into A. You will be get phi is equal to sigma into A and divided by epsilon naught. Yes or no? And total flux is what? Is 2EA. 2EA is the total flux. So it will be 2EA is equal to sigma into A and divided by epsilon naught. I hope now this is clear. This is comes from the after applying the Gauss's law. Clear? So solving this, you will be get AA cancel out, and the remaining term is E is equal to sigma upon 2 epsilon naught. Clear? Sigma upon 2 epsilon naught. Now here one question for you. Suppose if we increase the value of R, what will be the effect on E? If we talk about the field due to uniformly charged infinite plane sheet, what will be the effect on E? And if we increase the value of sigma, in that case, what will be the effect on electric field E? Second case. So first case is this one and second is this one. Please answer. In first case, what will be the electric field? So in first case, if we talk about the in first case, there is a no change. Electric field remain same. No change. Why? Look at here, this formula. The electric field due to a uniformly charged infinite plane sheet is equal to sigma upon 2 epsilon naught. This is the formula. Is there any R is present here? No, because if we talk about the electric field due to uniformly charged infinite plane sheet, E is independent of R. It not depends on R. Clear? So if we increase, there is a no change in E. What will be the answer of the second question? If sigma is increases, in that case, what will be the effect on E? What will be the effect on E? Think about it. Look at here. From this formula, E is equal to sigma upon 2 epsilon naught. It is clear that E is directly proportional to sigma. Now we know sigma is what? Charge upon area. Yes or no? If the sigma is increases, in that case, E increases. The value of E increases. I hope now this is clear. So third question for you, what is the graphical representation here? E and R. E and R. Here we talk about the, when we talk about the field due to uniformly charged infinite plane sheet. Think about it. What is the graphical representation? Look at here. This is on E, this is E and this is R. How we can draw this one? Look at here. If we increase the value of R, E same. If we increase the value of R increases, there is a no effect on E because it is independent. Clear? It is independent on E. I hope this is clear. One question for you. If we talk about there is a only one phase, only right phase. Right phase, there is only right phase which is positively charged. In that case, what will be the electric field? So if there is a only one phase, so the flux passing through due to one phase, due to this second phase, so in that case flux is what? Flux is equal to phi equal to what? Phi equal to EA. EA, because this is the flux through second surface, and flux through the first surface is what? Because there is a absence of charge. So phi equal to 0. Clear? Now using the Gauss theorem, total flux is equal to enclosed total charge enclosed by the closed surface divided by epsilon naught. Yes or no? And Q is what? Q is sigma into A. Now phi is what? Phi is equal to EA. So substitute the value of phi, because total phi is equal to what? Phi 1 plus phi 2. So here phi 1 is what? 0 and phi 2 is what? EA. So it will be equal to what? Only EA. So E is equal to phi equal to what? It will be EA divided by EA equal to total charge sigma A divided by epsilon naught. Now solve. EE cancel out, and remaining term is what? E is equal to sigma upon epsilon naught. Yes or no? If we talk about only one phase, and that is suppose the second phase, so in that case the electric field, the value of E, electric field due to uniformly charged plane sheet and the due to second phase of that sheet is sigma upon epsilon naught. Clear? And due to both phases, first phase and second phase, in that case E is equal to sigma upon 2 epsilon naught. Clear? So this is the main difference, and this is important for the exams. Clear? So vectorially, if we talk about in vector form, so E equal to what? Sigma upon 2 epsilon naught n cap. Look at here. And n cap is shows direction. Clear? Now if we talk about the electric field due to this single phase or we can due to this second phase, in that case vectorially E is equal to what? Think about it. Sigma upon epsilon naught and n cap, where sigma upon n cap is the magnitude or n cap is the direction. Clear? Here n cap is unit vector normal to plane containing outward. Clear? The field E points away from the plate for positive sigma and towards for it for negative sigma. It means what? If the sigma is positive, Sigma is positive. So direction is radially outward. Direction of electric field is radially outward. And if sigma, or we can say surface charge density, is positive, so the direction is away towards the point. Clear? Or we can say here E is independent of x. Look at this formula. E is equal to sigma upon 2 epsilon naught n cap. Is there any x is present here? No. X, there is a absence of x. So it is independent of x. If we increase the x so much, there will be no change on electric field. E remain constant. Listen carefully. Epsilon naught is also a constant value. Epsilon naught is also constant value. So only the factor on which the electric field is depend, that is sigma. That is what? Sigma. Clear? Now for finite large planar sheet, the result approximately hold in middle regions away from edges. So this is the all about the field due to a uniformly charged infinite plane sheet. And in next chapter, or we can say in upcoming lectures, we will learn electric field due to a uniformly charged thin cell. There we will learn what will be the electric field outside of the sphere, what will be the electric field inside of the sphere if the charge is distributed on the spherical cell. Clear? So in upcoming lectures we will learn. Here one question for you, and this is homework for you. Question is, if we increase the area, listen carefully, if we increase the area of this cross section, what will be the effect on E? Area is increases. Suppose the initial area when initial area is A, but we increase the value of A, it will be suppose A prime. In that case, A is the area of area A prime is greater than is as compared to A. In that case, what will be the effect on E? Think about it. So we know surface charge density, that is what? Sigma is equal to what? Charge upon area. Clear? Is if the area is increases, in that case what will be the value, what will be the effect on sigma? If area is increases, I repeat it, suppose sigma is equal to charge upon area. Here A increase, when we increase the A prime is increased. So what will be the effect on E? So we will calculate the effect on E from this formula, charge upon area. If area is increases, in that case sigma is what? Decreases or increases? This is homework for you. Clear? Thank you for your attention. That's all for the today's lecture. In upcoming lecture, we will learn about the electric field due to a uniformly charged thin cell. Thank you for your attention.